Right, there was only going to be 2 parts, but actually the other one went a bit long, so I've split it into 3 parts now. So this is part 3, which includes the Newton's law for cooling. Right, Newton's law for cooling says the rate at which an object cools depends on the difference in temperature between itself, meaning the temperature of the object, and its surrounding temperature, or the room temperature. Or in the case of maybe a fridge, the temperature of the fridge would be the surrounding temperature. This always reminds me of my son's 10th birthday when I cooked a chocolate cake in the morning, but it was something like 32-degree day or even hotter, and I actually couldn't cool the cake down to ice it, so we had to have an uniced cake that particular birthday. I just couldn't cool it down. Alright, so that's where Newton's cooling came into force. It had been a cooler day like it was other years, wouldn't have had a problem. So that was my experience with Newton and his cooling law. Alright, so what this means is that the rate of change of the temperature, so in this case capital T stands for the temperature of the object, TA, I've got T naught in this book, TA, we'll make it TA. TA stands for the ambient temperature. That is the room temperature, or the temperature surrounding. I'll put room temperature because it makes more sense, but sometimes if it's in a fridge or in an oven, the surrounding temperature would be the environment in which it's in. So TA, and they use A for ambient, the surrounding temperature. Okay, so we've got that, and of course little t is for the time it takes. So here we have our differential equation, and we need to integrate it. So once again, we need to separate the variables. Big T's and T's on one, big T's and DT's on one side, and small t's on the other. So we're going to take the t minus TA and put it there. So divide both sides by that number, and leave the constant r on the right hand side with the dt. Now we're ready to integrate. It's going to be a log of t, I better put the absolute value there, strictly speaking, the absolute value of t minus TA equals RT plus C. Alright, so we're going to take E of both sides, so the E of this side and the E of this side here. So T minus TA will equal, now the whole thing with getting a constant in front is the same as previously. So I'm going to put a C in front, or not a C in front, a K in front. K e to the RT, where e to the C will be equal to K, just the same as before. And so often they would put then T equals, and it doesn't matter where you put it, but say TA plus KE to the RT. So we have integrated our rate of change equation. So we now have what the temperature would be for the certain circumstances. We'll start off with the black coffee one. Let's bring on a question here. So black coffee is served at a cafe at 80 degrees C, which is too hot to drink. So after 2 minutes, it has cooled to 79 degrees Celsius. How long will it take to cool to 68 degrees Celsius if the room temperature is 21 degrees Celsius? Right, so usually it's best to go, what is it at the start? So the black coffee when it's served is 80 degrees, so at time t equals 0, we have 80 degrees when t is 0. All right, so we have the temperature is, how are we going to do this? The temperature is, oh, we should look at the surrounding temperature as well. The surrounding temperature is 21 degrees. Right, so we need to note the ambient temperature. Let's just pop that into equation now. I was thinking, what's missing? We need to put the 21 degrees in for the ambient temperature plus KE to the RT. So we are given that at time t equals 0, we have 80 degrees for the temperature of our coffee. equals 21 plus KE, and that'll be e to the 0. So 80 equals 21 plus K. And we can find what K is. 80 minus 21 will give us what K is. So 60, 59. So K is equal to 59. So we pop that into our formula. So we've got, we'll just leave the 21 there because it's going to be the same for this whole equation, where the ambient temperature or the room temperature is 21 degrees. But we now know that the K is 59. They also tell us that after 2 minutes it's cooled to 79 degrees C. 79 equals 21 plus 59 e to the 2r, because it's 2 minutes. So time is equal to 2 for 2 minutes. So I'm just reminding myself time in minutes. Right, so 79 minus 21, we get 58. So we've got 58 here equals 59 e to the 2r. Divide both sides by 59. And we get 58 divided by 59, very nearly 1, but it's 0.983 is equal to e to the 2r. We are going to log, whoops, don't write it down there. We're going to log both sides, so it's the log of this number times the log of that number gives us the log of 0.983 equals 2r, and of course we divide both sides by 2. The log of 0.983 divided by 2 will equal r. So putting that now into the calculator, we get an r equal to negative 0.0086. We've now found all our variables, so we know that T equals 21, where we've got our other one, 21 plus 59 e to the negative 0.0086 t, and it makes sense for that constant to be a negative, or that r value to be a negative, because it's cooling down. So the numbers are only going to go down with a negative value there. So it asks us at what temperature, sorry about the scrolling, how long will it take to cool to 68 degrees? So we're going to put 68 in here. We've got our 21, our ambient temperature, plus 59 e to the negative 0.0086 t. 68 minus 21 divided by 59, do a few steps together, equals e to the negative 0. Putting it in the calculator, we get 0.7966. And of course we need to log both sides. So the log of this will equal the log of that. So logging of E will just give you the number in the power. And of course last move is to divide by this number here. And putting it in the calculator, the log of 0.7966 divided by negative 0.0086, and we get 26. So T equals 26 minutes, which seems rather a large number for this to cool down from 80 degrees to 63. And the reason for that probably is that I made up the numbers myself. So probably it wouldn't take that long to cool to how long will it take to cool to 68 degrees if the room temperature is 21? Probably after 2 minutes it would be cooler than 79. So that's probably why the answer is a bit weird. So that's my bad, but the method is correct. Alright, so that's probably enough for now. I was going to do another couple, but I might just leave that for now and put this up on the Dropbox so that you can have a look at it.